Hello for the final time. Here it is, the last lesson in this course. So our final topic is something called infinite geometric series. So before we go to that, I just have some different definitions to talk about. So we know what a geometric series is, but there's actually two types of geometric series. They can be converging or diverging. So a converging series is when your absolute value, remember those signs? So we're not looking at the sign, just the value of it. So if your R value, the absolute value of R is less than 1, then we say it's converging because the terms keep getting smaller and smaller and smaller. And at some point, the numbers are so small that even though you're adding them to it, it's kind of negligible. They're so small, they don't have an effect to the overall sum. Kind of like adding the mass of electrons to that of protons and neutrons? No? Okay. So yeah, when you're adding a number that's really, really small, you're still adding it, but it's so small that it doesn't affect the overall value. So we say it's converging. Then the opposite would be diverging, when the absolute value of R is greater than 1, because those numbers get really big really fast. Okay, so let's look at an example of converging and diverging. So 1 plus 8 plus 64 plus ... Well, that's a diverging series. We know it's a geometric series. It's a series because we're adding. It's geometric because we're multiplying by the number 8 every time. So the R value is 8. 8 is greater than 1, so we say that it's diverging. So I worked out one fully, and then the rest I skipped some steps. So we're using the formula that we did last class off of your formula sheet. So it's the second last one on your formula sheet. The Sn equals T1, 1 minus R to the power of n over 1 minus R. So filling it in, what's the sum of the first three terms? Now, I used a formula, but really, 1 plus 8 plus 64, you probably got to that number faster. You probably had the answer before I even wrote this out. So yes, we realize you don't need a formula, but yeah, that does check out. So the first three terms, when you add them together, give you a sum of 73. Now, what if we add together the first 50 terms? So let's use the formula from yesterday. I didn't show my work because we just plug and chug, put the numbers in and solve. Then we get 2.0 times 10 to the power of 44. What? Why is that so big? Well, look, if we keep multiplying by 8, those numbers are going to get really big really fast. So this will be a huge number. What if we do sum of the first 100 terms? Well, that's even bigger, right? So that would be 2.9 times 10 to the power of 89. Where did I get these numbers? I just used the same formula we did yesterday. So just trust me. Well, or not, you can check it out on your own. So the point is, when you use have a diverging series, when the R value is bigger than 1, the numbers get big really fast. So they just keep getting, the sums will get bigger and bigger and bigger. But our final topic, we want to focus on the other one, the converging series. So converging is when your R value is less than 1. So 1 plus 1/3 plus 9 plus ... Our R value is 1/3, which is less than 1, so that means it's converging. So again, I worked the first one out fully. So what's the sum of the first three terms? Again, you probably don't need the formula. If you're good at mental math, 1 plus 1/3 plus 1/9 gives you 1.4. That's probably quicker, but I just used the formula from yesterday to show that it works. Our T1 times 1 minus R to the power of n over 1 minus R, yeah, they match. So you get the same number, same sum, whether you use the formula or you just added it up on its own. But look at the interesting part, right? So remember in our last example, the sums kept getting really, really big? Well, look at this one. The sums of the first 50, if I put in the formula, is 1.5. Well, how can that be? I have 47 more terms and it barely changes? Well, that's because the R value is so small, right? So even though I'm adding 47 terms, those 47 terms are so small that they barely have an effect on the overall sum. But look at this part. What if we do sum to 100? So we're going to add 50 more terms to it. Well, it hasn't changed at all. How is that possible? Because like I said, every time you multiply by 1/3, those numbers get smaller and smaller and smaller. It's so small, even though I've added 50 more terms, it doesn't affect the overall sum. So those are called converging. So again, if you looked at that, this would be 1 plus 0.3 plus 0.1. So we're already at 1.4. But look at, if that's already 0.1, think about how small all these terms are. So that's the difference between converging and diverging. And here we go. I know everyone's sad, but a very last example, sum to infinity and beyond, or whatever that is. Okay, our final formula off of the formula sheet. There's one we haven't covered yet, and it's the infinity, sum to infinity. So you know it's sum to infinity because it's the only one that has an infinity sign there. So that's our formula. So let's just do one last example and then that's it. 6 plus 3 over 2 plus 3 over 4 plus ... The pattern continues. So our first term is 6. The R value wasn't given, but hopefully we can tell that we are multiplying by 1/2. Now what's the n term? Well, when we solve to infinity, the n term goes on forever. So we don't have an n value. Our n value is infinity. So we use our formula, really simple compared to the sum formula we've been using last class. So the sum to infinity, our T1 value was 6, 1 is part of the formula, and R is 1/2. So again, 1 minus 1/2 is a half, 6 divided by a half is the same as, that's not 6.2, that's 6 times 2. Divide a fraction by a fraction, you multiply by the reciprocal, remember our rational unit, so 6 times 2 is 12. So that's a nice one to end with, but again, this formula only works when your R value is less than 1. So it does state that on your formula sheet. You can only do sum to infinity for converging series. And there you go, that's the pre-cal course. So before you get to your final assignment, I just want to congratulate all of you. This clearly, nothing in the world right now is ideal for anyone in any sense, but you guys have done a great job of hanging in there and persevering and doing your work and asking for help and completing your assignments. And I know that's not easy, right? It's hard to keep a routine. It's hard to keep motivated. But the fact that all of you have shows that you have a lot of maturity and commitment. And trust me, the hard work that you put in these last couple of months will definitely pay off next year for grade 12 and in the future when you go into calculus. So once again, I just really want to congratulate all of you. I've really missed you guys these last few months. We did our video conferences and we've had the emails, but that's not the same as being here in the classroom. So I miss the joy and the fun that you bring to my life every day. Now it's all been through computers and stuff, so I do appreciate the interactions we've had, but like I said, not ideal. But I hope you and your families are doing well. Don't forget to do your last final assignments. I'm done my lesson, but you guys still have this last assignment to do. But like I said, take care of yourselves over the summer, and hopefully when we come back in the fall, things can be a little bit back to normal. And don't worry about pre-cal 40S. I know some of you are really worried that it's hard, that you'll be missing concepts from this year, but really, I cut out word problems and mental math, everyone's favorite, but we got through all the key concepts. I did not cut out any outcomes at all, so we've covered all of them. So you should be fine, and like I said, next year we'll all be very sensitive to what we've all been going through, so we will make our adjustments in the fall time. But once again, just congratulations to all of you on making it to the end. So good luck.